All right. sFlow. Who's heard of sFlow or who uses it maybe on their routers? Oh, by the way, I run 3 different name servers on 3 different CCTLDs in 3 different AS numbers. And Nishal does not get to ask me any questions about this talk. Member of the RIPE community up north since about 1999. Participated in the 6-bone IPv6 network with NASA in the 1994-1995 era. That was fun. You can reach me at my Dutch email address, pim@ipng.nl, and also the obligatory Vanity Swiss one since 2006, and I moved to Switzerland then. In the pandemic, I got bored, so I incorporated a small company under ipng.ch, and we is really just I, because I'm the only guy that is in this company. And I develop DPDK and VPP, so these are router data planes that run on commodity hardware, just your PC or your rack-mountable server. And the European loop there you'll see is Frankfurt, Amsterdam, the north of France, Paris, Geneva, and Zurich, where I hail. So these things are all open source. They run VPP and a routing plane called Bird. There's 14 of them. We're the number 3, I think, best connected ISP in Switzerland, which is ironic because we don't do that much traffic. And we appear on the flap under AS 8298. So a little bit about sFlow. sFlow is this monitoring tool that doesn't try to be like IPFix or NetFlow. It just samples traffic, like 1 in 100 packets or 1 in 1,000 packets. Originally, sFlow version 5, which went through the IETF, and then I think, originally went through the IETF as RFC 3176, and then folks got bored of dealing with IETF, so they just split off on a website and said, we'll just publish all of our new specs over there. Currently at version 5. Mostly your data plane, your ASIC, and your switcher router will copy 1 in n packets from the data plane. Copy the first 128 bytes or maybe 256 bytes of it into a sample. And then every now and again, we'll look at the traffic statistics on these interfaces so you know how much total traffic there is. And then emit these samples together with these counters into a central host that will count them up. And it's actually pretty scalable. And it's very cheap on the ASIC because it doesn't have to have a lot of state. Doesn't have to know when the flow started and when it ended, and so compared to NetFlow, sFlow is significantly cheaper to implement. And as such, you can easily have 10,000 or even more routers and switches send their samples to one single central NetFlow collector or sFlow collector. And the heavy lifting then in analysis is not done on the box; it's done centrally in some upstream process or processing flow. So vector packet processing is an open source data plane that provides really, really fast networking, but just in user space on your Linux computer. And it uses libraries like DPDK or RDMA or VirtIO or AVF, like all of these ways that you can consume packets, and can easily, and I mean easily, exceed 100 million packets per second and 100 gigs or 400 gigs or even a terabit or more on a PC that you can buy today that is not even that expensive, at least not compared to the list price of a Juniper or a Cisco ISXR machine. So last year I was here and I gave an overview of VPP itself. That's the top link there. You can't click it now, obviously, but on the slides later you may want to take a look. There was a recording of that also. And there's a couple more talks that I did, one in the Netherlands about using only one IPv4 address because I don't have that many IPv4 addresses. Despite being in the industry for a long time, I never actually got an LIR until very recently. It uses all sorts of IP and Ethernet functionality, obviously tunneling, VXLAN, GRE, Geneve, but also MPLS. I was probably the last person to learn what is MPLS. I always skipped it until I built an MPLS plugin together with a friend of mine and presented that in Greece. And then in Barcelona, if you care about my tiny 4-digit AS number, you can take a look at how I built that network in Europe. So the way it works in VPP is packets enter as a bundle, as a set, this directed acyclic graph. And compared to a normal PC router that will take every packet and sort of move it through and then out on the interface or drop it or rate limit it or whatever. VPP leverages CPU cache lines to not do one packet at a time, but say do 100 or 200 packets at any one given time. So we ask the network card for work, it gives us a bunch of packets, and then all of them will go through this graph in together. And that means the first packet that goes into any one of these graph nodes may need to warm up the CPU instruction cache, but the second through 200th will actually find that all of the code that's run is already in the CPU's instruction cache, and so it becomes an order or 2 orders of magnitude faster, which is how we gain all this speed. So as we read from the network in one of these input nodes, we'll pass it on to typically an Ethernet input node. Obviously, if you don't have Ethernet, it will use another node, but this is the one that's mostly prevalent. So we go on to layer 2, and then that node's only job is to figure out, well, what type of packet is this? Is this maybe an IPv4 packet or an IPv6 packet or an MPLS packet? And then sends it off its merry way into those stacks or those parts of the graph. And this ends ultimately either in an output node, where we figured out what to do, we looked up the route, we looked up the next hop, we figured out which MAC address belongs to that on which interface, and then we're ready to marshal this packet out on the wire again. Or sometimes it ends in a drop, and these can be on purpose. For example, there's an ACL and you're firewalling this thing away, or there's a rate limiter and you decided to drop the packet, or there's actually an issue somewhere and it got dropped in any number of other ways. There's about, I'd say 40 different ways that VPP can end up dropping a packet. There's many of them. If you run complex or large networks, I think this is the #1 takeaway. Forget VPP. You want to always have a good view of where the packets did not end up going out of the switch or router. You learn a lot from that. So what we now do is we insert one of these nodes. We write them in C, and we insert one of these nodes into the graph. So you see here the gray input bubbles, and then the Ethernet input that I spoke of before, and we'll insert this sFlow node between them, which means we get a copy of that packet every time it goes through our node, and we can do something useful with it. Pardon me. And so we also want to do this on the egress path. So when we're ready to marshal the packet out, the green one at the bottom left there inserts between Ethernet output and interface output. And if we were to drop a packet, we insert it just before the ultimate drop where it gets bit bucketed by VPP. So there are 3 places where we insert one of these nodes. But they all kind of do the same thing. So the anatomy of this worker node. So the first part in the data plane is where we need to be very fast, right? Because the CPU is doing the routing for us. We can't dilly-dally because packets are behind us and they also need to go out very, very quickly. So the thing ostensibly takes the packet that it saw on the input and then moves it down to the next node, which would be Ethernet input in this case. But then for 1 in n, and these are marked in green, it'll just take a sample for further processing. It makes a copy of the first 128 bytes of the packet and then puts it in a lock-free and wait-free FIFO queue. And if the FIFO queue happens to be full, well, we give up and we drop the packet, right? So we're not going to try to overload the system if there's, for example, 100 million packets per second going through this interface all of a sudden. So we end up filling the FIFO queue, and if it's not drained fast enough, we drop them from the tail. And the goal is that the worker here spends as little as possible time processing these packets. And then the more expensive bits to process these samples into sFlow updates must happen somewhere else, not in the data plane. So the results that we got after a couple of iterations are pretty good. We spend roughly 9.5 CPU cycles in this node. And for reference, if you do an IPv4 routing lookup on any one given packet, on average, you take 211 CPU cycles in VPP. By the way, as an interesting side note, if you had a 2 gigahertz CPU, that also means you can do 10 million packets per second on one CPU thread. And if you were to have, say, 60 or 80 or 128 cores, you'll do 1 billion packets per second without problems. So adding 9.5 CPU cycles is not a terrible cost to pay for this feature in the data plane. If we do end up taking a sample, well, we have to copy it and put it in the FIFO, so it costs a little bit more CPU, and we clocked it at roughly 17 cycles for those packets that did get sampled. So then, they're in this FIFO queue, and in a different CPU thread that is not in the data plane, so it's not handling the forwarding itself, we flush every millisecond these FIFO queues, and then every 10 seconds, we ask the interface stats counters how many bytes and packets have you sent in the last 10 seconds. And if we were to drop a packet, we as well mark it as a dropped packet, right? And if it's on the input, we mark it input, and output mark it output. So this main thread is taking all of these samples from the FIFO queues of the workers and assembles these, they call it P-sample and counter datagrams, which we send to the Linux kernel using Netlink. And why do we do it this way? It's because it saves us a stack of code. Most implementations, also in merchant silicon, will use the sFlow daemon, which is a computer program written by Inmon that can read the samples from the Netlink channels, like the P samples and the counters, and then do even more heavy lifting, combining, creating UDP packets with them, sending them to the NetFlow collector on the other side. Right, and so this 3-layer cake keeps the cheapest operation in the data plane that has to run at 100 million times per second, and the most expensive one in the sFlow D daemon that ends up sending UDP packets to the central collectors. So I wanted to show you how I configured and tested this. So these orange bubbles are 2 machines. They're 2 Dell 730s. So they have Xeon E5 CPUs, some ECC RAM, and just 2 normal 10 gig network cards from Intel, the kind of famous 710s. So these will have 4 ports each, and they can do roughly 40 or 42 million packets per second on each card. And you can buy them for pennies on the dollar on the internet secondhand today. So I'll build 4 circuits, and for those that don't see the color, the top one here in cyan is a layer 2 cross-connect. So this means every packet I see on this one port, just copy it blindly to this other port in a cross-connected fashion, right, in both directions. And then the purple one is an IPv4 and MPLS forwarding. And then down below, the same, but without sFlow turned on. So now I can do a test with red and green with sFlow disabled to see how many packets per second make it through. And then at the top, I'll turn sFlow on and see how many packets per second do I get when sFlow is turned on. And it's to be expected that it will be less, because the CPU now has to spend these 9 CPU cycles inspecting the traffic and these 17 to build the samples. So configuration for IPv4, well, set the interfaces up, set some IP addresses on them. I'm going to set some routes on them just to the next hop, which would be the T-Rex load tester. And then these MAC addresses with the IP neighbor statements at the bottom are the MAC addresses of the load tester, so I don't have to do things like ARP resolution. I just know all the traffic goes back to the T-Rex load tester that I saw on this inbound port. So MPLS, one of my favorite features these days on VPP, create the table, turn on MPLS on the interfaces, and then just have a very simple label swap. In this case, these will be P routers. When I see label 16, I'm going to send it out on this interface and transpose to label 17 and vice versa. And so this would just be a layer 2 or 2.5, I guess, MPLS bridge on the 2 interfaces. It's very simple to set up, and it's actually surprisingly quick. And then the layer 2 cross connects. Many vendors have this as well. The syntax for it here is turn the interfaces up and then set both the interfaces in a pair in layer 2 cross connect mode, and then tell 10 gig Ethernet 302 to cross connect into 303 and 303 back into 302, which just essentially makes a cross connect between these 2 ports. And again, green will have no sFlow enabled, and the light blue cyan will have sFlow enabled. And then the sFlow itself, here's the configuration syntax for it. You can turn on a certain sampling rates. That can be 10, 100, 1,000, a million. So that would be 1 in a million. And then the direction, either only ingress, only egress, or both directions. Drop monitoring on or off to also see packets that never made it through. Polling interval is for the interface counters. The nice thing about the statistics here is if you sample the interface counters every 10 seconds and 1 in 10,000 or 1 in 100,000 packets on a 100 gigabit Ethernet interface, you will get a statistically valid representation of the traffic through it. So you really don't have to see all the packets at all. And then turn them on these 4 interfaces at the top there. So this is on the top right machine called Hippo because it's always hungry for packets. 10 gig 300 through 003 all get the feature turned on, which means the bottom ones there on 10 gig 130, 0 through 3, keep it turned off. So then the sFlow D, that's the third component here that we have to configure, is the daemon that runs just on the Linux side. And I'm going to send collection samples here to 2 destinations. One will be localhost on this UDP port 6343, which is the default sFlow port, and then a second collector sending datagrams also to localhost, but in a different namespace. So this feature allows you to send the UDP sample packets to both the internal management network as well as within the data plane through VPP onto the internet if you'd like. We send samples to sample group 1, small detail, and then we turn on the VPP collector with that little stanza VPP there. So as soon as we start the sFlow D, we can run this tool called sFlow tool, which listens on this UDP port for the ultimate packets, right? So at the end of this whole game, the packets are being seen here as UDP datagrams that you can do further processing with. A couple of notes here. They're maybe not super important, but if you did venture into this VPP and sFlow, they will maybe bite you. Most VPP instances run in a separate network namespace, typically called data plane. So it's very important to make sure that the sFlow D listens to the correct network namespace for those netlink packets that come from VPP. Otherwise, you might end up seeing none. You can choose which one to use, or several, which I showed in the previous slide, with these collectors that are either running in the default namespace or in a named namespace like data plane. I also contributed to Linux control plane support, whole different talk. Interface IDs will be emitted typically with the interface index from VPP, right? Because if you remember, Linux no longer has the network card, so it doesn't have any interface index for it. And if the Linux control plane is loaded, then we'll use its version. If it is not, then we will use the interface ID from VPP itself. And they don't have to be the same number. Those are 2 different namespaces. Okay, so 2 more things. One is the performance of it. Last year I stood here with the exact same picture. This is a favorite computer of mine. This is Hippo. And it's a 730 that I bought secondhand. Originally in 2012, I bought it maybe in 2022. It was not very expensive. And I'll show you the output of T-Rex if you've ever used it. It's a load tester. You can do stateful and stateless load testing with it at pretty high rates. And I've used the colors here to show which interface pairs are what. So this corresponds to the graphic that I had a couple of slides ago. So the IPv4 MPLS with sFlow turned on does 23.6 million packets per second in this load test. And without sFlow turned on, it also does 23.6 million packets per second, and that's because this thing is doing line rate on all 4 ports with 1 in 10,000 sampling on or off, doesn't matter. So it's forwarding 80 gigs of traffic now with very small packets. Here's a table that shows it in a little bit more detail. Layer 2 cross connect, which is the cheapest thing you can do. You got the Ethernet frame here, you just like moved it to this other port over there. The line rate of a 10 gig network card with the smallest packets we're allowed to send, which would be 64 bytes, is 14.8 million packets per second. And you see here that without sFlow turned on, it actually does 14.8 million packets per second on 1 CPU thread. And this machine has, I think, 88 CPU threads, so it's a beast. It will do a lot of packet forwarding. If I turn on sFlow now, so this second row here, it drops to 14.3 million packets per second on 1 core. And that's because now we have to inspect every packet through this graph node, which takes 9 CPU cycles per packet, right? So it's not entirely free. But then if I ratchet up the sample count from 1 in 1 million to 1 in 10,000, and even all the way up to 1 in 100, it doesn't drastically get worse. So we still do 14.15 million packets per second on 1 CPU thread in layer 2 cross connects. So for IPv4, it's about 10.8. if you're 10.9 if you don't have sFlow turned on at all, and 9.7 if you have it turned on. And there's actually an interesting statistic as well in this last row. If you send 1 in 1 million packets, well, you have 337 million packets, I guess, per minute. 328 of them were sampled, like 1 in 1 million, and then 328 were actually processed and sent. But if eventually this FIFO queue gets full, I mentioned we'll drop them from the tail because we don't want to overload further processing. And that's what you see in the 1 in 100 case, where we sampled 3.3 million and then found we can't actually move them all into the FIFO queue. So we drop 1.81 million of them, which means 1.53 million still get sent through. So if you don't do something bizarre, like 1 in 100 sampling on a 10 gig network card, you're totally fine. That's the takeaway. And we did not manage to crash anything because VPP does pre-allocation of every single buffer, never does a malloc, never runs out of memory. So that either fits or it doesn't. It's really cool. So the demos that were spoken of are just screenshots. There's no risk for me falling on my face today. I'll do that maybe another day. Interop. So Inmon is the original author of the sFlow specification, and they own a bunch of the IP, but also a bunch of the open source code on it. They have this tool called sFlow Realtime, which you can run inside of Docker that consumes all these UDP packets and shows you some graphs. The thing Yolandi struggled with is, ntop. It's a thing written by Luca Deri in Italy. ntop is a tool that you use normally on your PC, your Linux server, and there's an ntop ng, it has no relation to ipng, which shows this as well. And this is a live screenshot with blue and green from just a test that I was doing with some synthetic traffic. And then everyone's favorite, not necessarily mine, is Akforado. Akforado is, again, an open source tool that allows you to consume NetFlow, sFlow, all sorts of sampling data, and draw them and slice them inside of a real-time database. You can see how much traffic came from which AS. Completely open source, very, very fun to play with. And again, it looks very synthetic, but this is just a load test that I was putting on the bench by ramping up and down traffic with T-Rex and then seeing what came out on the other side. So it's all real data. That's what I got. One nerdy picture in the end. The 1.8 kilowatt 3 machines that were doing 1.25 terabits per second, and I think 970 million packets per second on one VPP instance in the middle there, being ganged up by 2 load testers, because interestingly, VPP is faster than the load tester itself, and so I needed to get more machines. Thanks to my buddy Vlad for providing them, because they're very expensive in the end. And also mad props to Neil McKee from Inmon, who wrote 90% of this code. I just helped package it up for VPP. If you'd like to give it a go, come find me. I'll be around. And if there's any questions, we got, I think, 3 or 4 minutes left.
Any questions for Pim? Not Michelle. All right, cool. Well, Pim,
thanks a lot.
thank you so much.
Thank you.
All right, yeah, thank you. All right, so that is our wrap.